So, ladies and gentlemen, I'd like to welcome Bill Hanlon for the next session.
Okay, thank you. All right, so today what we're going to do is looking at how we can connect what's being taught in elementary school to what's being taught in secondary school. I would tell you the biggest difference between elementary school, the math taught, and high school, and particularly in algebra, is mostly vocabulary and notation. So what my intention is to kind of walk you through a number of examples for two reasons. One is, if in fact you're an elementary school teacher, you need to know the stuff that you're teaching is going to impact what students will learn later. And for secondary teachers, it's important for you to know how to link what they're teaching to what you're currently teaching, because the whole idea is that we make students more comfortable in their knowledge and their understanding of math. And the way we do that, to be quite frank, is through linkages and through using, and this is the important part, using simple, straightforward examples that work, that clarify what you want them to learn, and then don't bog them down in needless arithmetic. So let's go ahead and get started. Now, if I go off the page or you don't understand something, please, or if I make an arithmetic mistake, please jump in right away. Don't let me just continue to babble on if I said something like 4 plus 3 is 12. Okay, so in elementary school, we have problems like this, 432, and we ask the students to write that in expanded notation. So that's 4 times 100 plus 3 times 10 plus 2 ones. In an elementary school, we call that expanded notation. Later, what we do is we show them how to write that without the X for times, and rewrite that as 4 times 100 plus 3 times 10 plus 2 times 1. Then, of course, they learn about exponentials. So they learn to write this as 4 times 10 squared plus 3 times 10 plus 2 times 1. And then we might say to them, let's let n equal 10. And we rewrite this as 4 times n squared plus 3 times n plus 2 times 1, I'm going to call 2. And then we get to a class like algebra, and we say we're not going to use the dot anymore, and we like to use x's. So we're going to rewrite this as 4x squared plus 3x plus 2. The greatest thing that changed here is the vocabulary and notation. We started off in elementary school as 4 times 100 plus 3 times 10 plus 2 times 1. We changed the multiplication sign to a dot. Then we can change, we said let n equal 10, so we use substitution. And then all of a sudden, instead of saying 4 times x squared, we're saying 4x squared plus 3x plus 2. And we're using exactly the same concept that we use up here, except up here it's called expanded notation. In an algebra class, of course, this is called a polynomial. All right, now I can't make math any more difficult, but with little kids, if the kids understand place value and we have a problem like 341 plus 256, what we have the kids do is they say we have 3 plus 2 100s. We have 4 plus 5 tens. And then we have 6 plus 1 ones, which turns out to be 500s plus 9 tens plus 7. And if we multiply that out or add that together, that becomes 597. Well, what does that look like when they get to an algebra class? 341 looks like 3x squared plus 4x plus 1. And we're going to add that to 256. In an algebra class, that looks like 2x squared plus 5x plus 6. In elementary school, we tell kids add the hundreds to the hundreds, the tens to the tens, and the ones to the ones. Now what we're going to do is we're going to combine what we call like terms, which means we're going to add the x squares to the x squares. We're going to add the x's to the x's. So just like up here, I'm going to take my x squares and I'm going to have 3 plus 2 x squares plus 4 plus 5 x's plus 6 plus 1, which is 7. And when I rewrite that, that's going to become 5x squared plus 9x plus 7. Notice down here, in elementary school, I'm adding hundreds to hundreds, tens to tens, ones to ones. Down here, I'm adding x squares to x squares, x's to x's, and numbers to numbers, except we don't say that. What we tell kids is combine like terms. My point is this, just like with expanded notation and polynomials, the biggest difference is the vocabulary and the notation, how we say it and how we write it. Combine like terms actually means add the hundreds to the hundreds, tens to the tens, ones to the ones. And so the math itself doesn't change. If I want to teach multiplication of binomials, if I have a problem like 32 times 21 that's taught in elementary school, we go with expanded notation. 1 times 32 is 32, 2 times 32 is 64. We draw a line and add and get 672. In algebra, what does that look like? 32 is 3 tens plus 2 ones. I'm just going to rewrite that as 3x plus 2. The 21 is 2x plus 1. And as I multiplied 1 times 32, I'm going to multiply 1 times 3x plus 2 and get 3x plus 2. Notice the partial product. Here are the digits of 32. Here the coefficients are 3 and 2. I indent a space and multiply, so I get my 6x squared plus 4x. And notice here's my 6 and 4 for my partial product. Here's my 6 and 4 from my partial product. I draw my line and add, I get 6x squared plus 7x plus 2. So the point I want to make is the algorithm, a standard algorithm that's taught in elementary school, is also going to be used to introduce multiplying with polynomials. Then what we do in algebra is we have a tendency to look at that horizontally. So I'm going to write this as 2x plus 1 times the 3x plus 2. And the way we do that is we multiply the 2x times both of those numbers, then we multiply the 1 times both of those numbers. So 2x times 3x is my 6x squared, 2x times 2 is 4x. And you can see that was my partial product that I had before. Then I multiply by 1, 1 times 3x is 3x, 1 times 2, is 2. And then I combine like terms, I get my 6x squared plus 7x plus 2. So these algorithms that we teach in algebra come directly from the elementary standards that we do in the math. Okay, let me just say this, if I got some chats here. Okay, all right. I'm blind, so if you write something and I don't respond to it, yell at me. Okay, so let's go ahead. So now the point that let me get back over here because I can't find the damn thing. All right. And there I am. Okay, so the point I want to make is this. The math that you teach, particularly in algebra and geometry, is math that has already been taught. You need to understand that. From an elementary perspective, you need to know what you're teaching. Those teachers rely on to be able to use it. So, in elementary school, as you learn how to do prime factorization and all that kind of good stuff. Is that important? The answer is yes. Let me show you why. In high school, if I want to factor a polynomial like x squared plus 19x plus 48. Okay. Well, what a lot of teachers do, I don't know why, except that they don't want to drive kids crazy. They make a big X over here and they do a lot of crap. Okay, so what I'm going to suggest to you is when you have a constant like 48, you come off to the side, write down 48. And now what we're going to do is use division by primes and the multiplicative inverse. So I'm going to write 48 as a product, 48 times 1. I'm going to divide that by 2 and have that 24 times 2. So if I divide this by 2 and multiply by 2, that's the multiplicative inverse, which means I'm multiplying by 1. If I divide this by 2 and multiply that by 2, notice I still get 48. If I divide this by 2 and multiply this by 2, I still get 48. If I divide this by 2, multiply this by 2, come on, Hamlin, you can do that. That's a 16. All right, then these are, and I can't divide by 2 anymore. Okay, so if I ran out of factors, what I could do is I could start dividing this by 3, the next prime number. Now, in terms of algebra, if you write down all those factors, you say which ones of these add up to 19. That adds up to 49, 26, 16, 16, and there we go. 3 plus 16 is 19. So this is a factor of x plus 3 times x plus 16. So using prime factorization and factorization helps you get that. Now, how do I know if I have all the factors? Well, let's do our prime factorization. 48 is 6 times 8. 6 is 3 times 2, and 8 is 2 times 2 times 2. To know if I have all the factors, I rewrite this as 2 to the 4th times 3 to the 1st. All right. And in terms of doing that, I have, if I add 1 to each of these exponents, so the exponent here is 4, I add 1, I get 5. This exponent is 1, I add 2, I add 1 and get 2. If I multiply 5 times 2, that will tell me how many factors there are in the number 48. So you can see I'm going to say 5 times 2 is 10. And let's see if I have them all. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, from elementary school, learning how to do prime factorization and dividing by primes, I can find out all the factors. And if I'm not sure I got them all, what I can do is use prime factorization, add 1 to each exponent, and find that product. And that should tell me how many factors I have. So let me just give a different one. So I have to divide out by another number. Let's say I have a problem like x squared plus 23x plus 60. Okay, now I know some of you can factor that very quickly in your head, but the way we do that, if you're looking for a systematic approach to finding the factors, that's 60 times 1, divide by 2, which is 30 times 2, divide by 2, which is 15 times 4. I can't divide by 2 anymore, so what I'm going to do is my next prime number is 3. Divide 60 by 3 is 20. And what did I just do? And multiply by 3 is 23. So, whoops, there I am. So there's my factors. Now, is that all the factors? The answer is no, because if I took 60 and rewrote that as 10 times 6, this is 2 times 5 times 2 times 3. So the factors are 2 squared times 3 times 5. If I add 1 to each exponent, that's 3. This is 2. This is 2. So we'd know there's 3 times 2 is 6 times 2. We'd know there's 12 factors in 60. I only got to 8 of them because I'm going to stop right there. Okay, now, once I get to this, I can go ahead and start now dividing by 2 again, get 10 times 6, and then divide by 2, 5 times 12. So I divide, multiply by using the multiplicative inverse. The point that I want to make is little things like prime factorization that you do in elementary school is going to affect how you do factorization, polynomial factoring in high school. The nice thing about math is it's so connected. I'm trying to go fast here, so if I'm going too fast and you need me to slow down, just yell at me. Okay, let's have you all add fractions in your head, but also not only adding fractions in your head, let's see how you can do that using rational expressions. Oftentimes, when I'm talking to secondary math teachers, they say things like, how the hell can I teach kids how to add rational expressions? They can't even add fractions. Okay, I got it. But if you use linkages, you can go back and review and reinforce and address any deficiencies they have. So let's start what they do in 3rd grade. Let's say, and I'm going to start off with unit fractions because I always start off with simple, straightforward examples that work, that clarify, that kids go, oh God, got it, that was too damn easy, and then I scaffold. So let's say I have a problem like 1/3 plus 1/2. In little kids school, 1/3 looks like this up here. 1/2 looks like this. I can't add those together because the definition of a fraction is it's part of a unit made up of 2 parts, the numerator and denominator, and the denominator tells you how many equally sized pieces, how many equal parts make one whole. These are not equally sized pieces, so I can't add them together. So what I'm going to do is I'm going to take this cut and put it up here. I'm going to take these 2 cuts and put it down here. And now when somebody says, how many pieces do I have? Now you can say I have 2 out of 6. And here you can see I have 3 out of 6. And if I say, well, how many pieces do I have altogether? I can count 1, 2, 3, 4, 5. I have 5 pieces altogether. And how many pieces make one whole unit? That's 6. So when some kids want to add 6 and 6 and get 12, besides slapping them upside of the head and say, you can't do that, the reason you can't do it is definition. The definition is the denominator tells you how many equally sized pieces make one unit, not 2. Okay, so let's say I did 2 or 3 of these problems. After I did 2 or 3 of these, what I would do is introduce math speak. So here we made equally sized pieces and we renamed it, and then we counted how many pieces we had. But what we do is after we do a few of those, we develop an algorithm. We tell kids to add or subtract fractions. What do? You find a common denominator. Second, you make equal fractions. Third, you add or subtract, come on, Hanlon, the numerators. Fourth, you bring down the denominator. So what you do is you build an algorithm so the kids are acquiring the language that's important to math. And I have to tell you, what causes kids difficulty in math has nothing to do with math. It has everything to do with not knowing vocabulary and notation. So let me get off this for a minute and just give you an example of that. If I gave you this here, 8x squared, y cubed, z to the 5th, and if I ask the average student, what is the degree of that monomial, I would get a bunch of blank stares. But as you know, to find a degree, all you do is add the exponents. 2 plus 3 is 5, plus 5 is 10. The degree is 10. My point is this. If kids couldn't do that problem, it has nothing to do with the math. It has everything with not acquiring the language. Okay, back to the fractions. We said would find a common denominator, make equivalent fractions, add, subtract the numerator, bring down the denominator, and simplify. Well, that works out fine. If I have problems like this, 3/5 plus 1/4, I can find the common denominator pretty easily by multiplying. I can make equivalent fractions. 5 times 4 is 20, so 4 times 3 is 12, 4 times 5, that's 5. So I get my 17/20ths. So adding fractions, piece of cake. But now what happens is this. What if I have 5/18 plus 7/24? What do we tell kids to do? I swear to God, what we tell people to do, we tell them to multiply. Are you kidding me? We're going to multiply 18 times 24 and come back to this problem this week. The next way we tell people to do it is to write multiples. What kids are you teaching? What kid do you know can write, goes 18, 36, 54, 72, 90? Hell, they can't skip counting tens, never mind 18. Skip counting is how you're going to find a common denominator? I don't think so. Do you hate kids? Are you going to make them do it the least common multiple? Are you serious? That's how you're going to find a common denominator? Hell no. What you're going to do is you're going to show them the reducing method. Now, what the reducing method comes from the least common multiple. But in the reducing method, all you do is you put the two denominators over each other, either 18 over 24 or 24 over 18. I don't care which it is. You reduce. Well, now you call it simplifying, but that screws up my jokes. So I'm going to simplify this. This reduces to, it simplifies to 3/4. When I cross multiply, 3 times 24, 3 times 20 is 60, 3 times 4 is 12, 60 and 12 is 72. My common denominator is going to be 72. And as you know, 4 times 18, 4 times 10 is 40, 4 times 8 is 32, 40 and 32 still gives me 72. Now, what's nice about using the reducing method, when I say 18 times what gives me 72, whoops, there it is. It's right there. It's 4. So 4 times 5 is 20. If I say 24 times what gives me 72, it's right there. When I cross multiply, it's 3. So 3 times 7 is 21. So bottom line is, if you understand the at least common multiple, you can find the common denominator by simplifying. Now, let me get back to the fractions. We said a minute ago, 1/3 plus 1/2. We said that answer was 5/6. If I was working with kids, I would give them some more problems like 1/4 plus 1/5. We would find out that answer is 9/20. And if I had a problem like 1/4 plus 1/3, that answer is 7/12. After I drew these pictures and had the kids add those, I would ask them, can you look at this problem and tell me where the 6 came from? Can you look at this problem and tell me where the 20 came from? Could you look at this problem and tell me where the 12 came from? And most kids would say, yeah, I get it. Now I could say to them, well, look at the same problem. Can you tell me just by looking where that 5 came from? Can you tell me just by looking where that 9 came from? Can you tell me just by looking where this 7 came from? And most kids are going to go, oh, dang, why am I doing it the long way? Because now if I said to them, what is 1/10 plus 1/3? What they're going to describe is to get the denominator, they're going to multiply. To get the numerator, they're going to add. And the answer is 13/30. And of course, when you do a problem like that in math, you always typically end it with the POC. Okay, everyone knows what POC stands for in math. This is very important notation. Okay, it stands for piece of cake. There you go. Now, after I do a bunch of those with unit fractions, what I'm going to do is instead of having unit fractions, I'm going to throw different numbers in there. So let's say I have a problem like 3/4 plus 1/5. I know my common denominator is going to be 20. My numerator is going to be 19. If I had a problem like, let's say 1/10 plus 3/7, my common denominator is going to be 70, and my numerator is going to be 37. If I have a problem like 2/5 plus 1/3, my common denominator is going to be 15, and my numerator is going to be 11. So now I'm going to ask kids, do you see where the 20 came from? Do you see where the 70 came from? Do you see where the 15 came from? And again, most kids are going to do that. Now, when I ask them, where did this 19 come from? This doesn't jump out at you. Where does this 37 come from? So what I'm going to ask kids to do is you can't stand there and stare at this sucker. You got to play these games. You have to multiply, move stuff around. So is there any way I can get a 19 by combining these numbers somehow? Is there any way I can get a 37 by somehow combining those numbers? Is there any way I can get 11? And if I had more time, we would let the kids find that. And what you start to realize is if I multiply 1 times 7, that's 7. 10 times 3 is 30. Oh my God, that gives me 37. Same thing down here. If I multiply diagonally, 3 times 5 is 15. 4 times 1 is 4. I get 19. Unbelievable how this all works out. Same thing here. 5 times 3 is 15. 2 times 3 is 6. 5 times 1 is 5. 6 and 5, sure enough, gives me 11. So now if somebody says to me, what is 3/4 plus 1/7? I know my common denominator is 28, and then I'm going to multiply diagonally. 3 times 7 is 21. 4 times 1 is 4. 21 and 4 is 25. So what we do is we generalize that now. What if I have algebra like 2 over x plus 3 over y? Well, my common denominator is x times y. My numerator is 2y's plus 3x's. Okay. Now, what's nice about math is you can never make it harder. You can only make it longer. So let's say I have a problem like 2 over x minus 1 plus 3 over x plus 2. My common denominator is going to be x minus 1, x plus 2. My numerator is going to be 2 times x plus 2 plus 3 times x minus 1. Okay. When you get done with those problems, you normally make a little happy face. And if you want, you can put eyebrows with it. There's the little nose. But anyway, you look at this stuff and you think, okay, what have we done? You know, if I talk to a lot of teachers teaching algebra, they're thinking, I'm supposed to add rational expressions. The kids can't add fractions. If you link it and you use simple, straightforward examples that work. So what we did, like with this fraction stuff, we looked at drawing pictures to add them. Then we changed that to math speak. We build a math algorithm so the kids are acquiring the language. Then what we did is we went from unit fractions, we scaffolded to not unit fractions. And then we scaffold again to, oh my God, algebra. And, you know, and then here's the nice thing about this. If you do it and if you develop it, now when the kids see something like this, you know, because in a lot of algebra books, this is what you get. You get A over B plus C over D is equal to AD plus BC all over BD. You know, kids look at this and go, what the hell are you talking about? But if you showed them where that came from, then they'll be able to add those fractions or rational expressions very quickly. So here's my point is, if your book used A over B plus C over D and the kids memorized AD plus BC over BD without understanding, what would happen if they had R over S plus T over V? If they saw it develop, they'd know that SV is the common denominator, and that would be RV plus ST. So if they see it, then the variables that you use makes no difference. Okay. Do me a favor, because I know I'm going like a bat out of hell here because I don't have a whole lot of time. So if you're okay up to this point, put down okay in your chat. If you're not okay, put down an N. So you need to see an okay or an N. Okay, there's 55 of you, so I'm going to use this idea of one-to-one correspondence. There should be 55 okays or with N's. Okay, everyone is okay with that. Everyone's lying to me. Nobody ever wants to talk to me. Okay, why do math teachers talk to themselves? Come on, people. It's because they think somebody's listening. I don't want to explain these things to you. Okay, you're walking down the hallway. You see some kid with snot hanging out of his nose or something, and you say to one of your colleagues, oh, wow, that kid is 288. What does it mean if you call somebody 288? Come on, people, this is math. You need to know this stuff. Okay, if you have 12 of something, what's that called? A dozen. Thank you. I'll talk to myself. If you have 12 dozen, that's 144, right? So what happens if you have 288?
Too gross.
It's too gross. Okay, for those of you who don't know math jokes, you need to go to my website under math and look under humor so you can get some of these. How the hell can you have a party at your home if you don't know math jokes? My God. All right, so let's go back to elementary school. In little kids' school, how many, do I have any element? Do me a favor. A lot of you are not on screen. You got names here. So I can't read, I can't read your body language. It's a good thing I'm not, I teach the RPDP classes. If you're somewhere up north and you're not taking them, then go to the Southern Nevada RPDP website and sign up for the damn things. They're free. They're used for CUs. And if nothing else, you'll be entertained. All right, where am I at now? So bottom line is this. We teach equations. This is what equations look like when in second and third and fourth grade. You have 2 times, and then they have a circle, plus 3 equals 13. And then the kids have to guess what number goes in the circle. So they try 1, and then they try 2, then they try 3. They finally get to 5, and they put the little 5 up there, and now they're happy as it can be. Well, what does this problem look like as the kids get into junior high and algebra? 2 times the circle, which is what they put number in, now looks like this. 2x plus 3 equals 13. So this is how they're solving equations in primary grades, intermediate grades, and this is what it looks like in high school. Well, and how do we get these? Well, somebody has a problem like this, 2 times 5 plus 3. They use the order of operations, which is nothing more than agreement, kind of like driving on the right-hand side of the road is kind of an agreement, unless you want to meet new friends. If you watch a ball game and it says, Boston 5, LA 2, and if I say, where is the game being played? Well, the agreement is the home team is always listed second, so we know the game is being played in LA. So when we have a problem like this, a reasonable person could look at 2 times, let me write it this way, 4 plus 6 times 2. A reasonable person could look at this and say 4 plus 6 is 10 times 2 is 20. Another reasonable person could say 6 times 2 is 12 plus 4 and get 16. The problem with that is we have one problem with 2 different answers. In arithmetic and computation, we don't allow that to happen. The closure property guarantees one and only one answer. So we have to come up with a way so everyone does this the same way, and that's called the order of operations. So we use that. Please excuse my dear Aunt Sally business. Or we say, what the hell's the other one called? God, I forgot what it's called. PEMDAS. Yeah, it spells PEMDAS. That's what it says. Okay, but anyway, here's the way you get this expression. So what we're going to do now is we will do anything that has parentheses. We don't have any exponentials. We have a multiply, so we do that. 6 times 2 is 12, plus 4 is 16. So now we're going to agree that this is the answer. Now, if I gave you directions to my home and you wanted to use those same directions to go back to your house, you'd use the directions I gave you and go in reverse, doing just the opposite. Or I could, let's say I gave you a present. If I gave you a present, I'd take the present, put it in a box, put a cover on the box, put paper on, put tape on, put a bow on. Okay, what would you do to get the present out? Take the bow off, take the tape off, take the paper off, take the cover off, and take the present out. In other words, you would go in reverse, undoing what we have done. So, and if we're going to undo an expression in math, we call that solving an equation. So a problem like this, if I get back over here, if I want to be able to solve an equation, what I have to do is I'm going to have to take the order of operations in reverse using the inverse operation. So if I have this problem here that we just did in little kid school, and we wrote that as 2x plus 3 equals 13. Well, when kids are doing this, 2 times what number plus 3 equals 13, when they're doing that in elementary school, the answers always come out to be nice whole numbers. So they're going to be like 2, 3, 5, there's going to be nice numbers. As you get into later grades, we could get fractions and decimals and all kinds of other stuff. So guessing would not be a great way of doing that, trial and error. So we come up with a systematic approach. And what is a systematic approach? Is equations in the AX plus B equals C format. So AX plus B equals C format. When you have equations that are in that format, we use the order of operations in reverse. So we have a problem like the 2x plus 3 equals 13. What I'm going to do is, using the order of operations, which is the please excuse my dear Aunt Sally, going in reverse, I'm going to get rid of any addition or subtraction. So here's my problem, 2x plus 3 equals 13. How do I get rid of, I have an addition, how do I get rid of it? I subtract 3 from both sides. So now I have 2x plus 0 equals 10. Now, 2x plus 0 is 2x. That's just by identity. So 2x equals 10. I don't have any other addition or subtraction. So I have a multiplication. How do I get rid of that? The opposite. I divide by 2. So x is equal to 5. So what we do is we take what the kids have learned, like problems like 4x minus 2 equals 18. And we use the order of operations in reverse. So we get rid of any addition or subtraction, then we get rid of any multiplication, division, then we get rid of any exponentials and parentheses. So I look at this, and this is in the AX plus B equals C format. So I look at this and I say, I have to get rid of any addition or subtraction. I have a subtraction of 2, so I'm going to add 2 to both sides. So I get 4x equals 20. I now look at this and I have a multiplication. How do I get rid of a multiplication? I do the opposite, divide by 4, divide by 4. So x equals 5. Now, the nice thing about math is you can never make math more difficult. All you can do is make it longer. So if I have a problem like this, 8x minus 3 equals 6x plus 9. What I ask the students is this in AX plus B equals C format? So the first thing I'm going to ask students to do is identify what is different about this problem. That has nothing to do with their math ability. It has to do with, can they tell what's different? Well, here I have a number in front of an x plus a 3 equals, well, what I have here is an extra thing here. So what do I have kids do? I have them identify it. Now, once you identify what's different in a problem that is not in the AX plus B equals, the hell is going on here? Why isn't that thing changing? Mike, make sure you tell me what time it is if you don't mind. Don't let me keep going. Once you realize the problem is not in the AX plus B equals C format, what you do is you do what I call using the get rid of it strategy. If you have a problem that has a radical in it, how do you solve it? You get rid of the radical. If you have absolute values, what do? You get rid of the absolute values. If you have systems of equations, if you have 2 equations, 2 unknowns, what do? You get rid of an equation. So in math, we use the get rid of it strategy. And the get rid of it strategy is everything comes back to AX plus B equals C. If you have a logarithmic equation, what do? You get rid of the logarithms. If you have an exponential equation, what do? You get rid of the exponents. You get rid of the exponentials, excuse me. So if you have a quadratic equation, what do? You end up rewriting that as a factored form, ax plus b equals c, but now you're going to have c equal to 0. So anytime you're solving equations in math, if you're not teaching the ax plus b equals c format, start today. Okay, having said that now, what you do is you have the students look at a problem they don't know how to do and say, what's bothering you? They identify what's bothering them and you get rid of it. Now, the trick is you get rid of it by using the properties of real numbers, not an eraser. That's the trick. Now, once you have identified what's bothering you, you get rid of it. So you look at a problem like this. If I can get back on there. Yes, I can. I have that 6x over there, which is not an ax plus b equals c format. So I'm going to subtract 6x from both sides. So in terms of subtracting 6x from both sides, 8x minus 6x is 2x minus 3. The 6x minus 6x disappears, and that's equal to 9. And then lo and behold, I have a problem in the ax plus b equals c format. So now I use the order of operations in reverse. How do I get rid of a minus 3? I add 3 to both sides, so 2x is equal to 12. How do I get rid of a multiplication? I divide, so x equals 6. Again, piece of cake. I can't make math more difficult. All I can do is make the problems longer. Now, when you're teaching, notice the numbers that I'm using, how they all came out nice. When you are teaching, if you're using simple, straightforward examples that work, this is what kids should be doing. Got it, got it, got it. Don't be putting stupid numbers in the damn problem where the kids off to the side doing arithmetic and concentrating on something like that, as opposed to learning the concept of skill you're trying to teach. That's important. And that can't happen unless you pick your simple, straightforward examples that work. Okay, so I don't care what you're teaching. It always comes back to ax plus b equals c in terms of equations. And if you think about it, it just makes it a whole lot nicer. Okay. Again, a point that I want to make is the biggest difference between elementary school and secondary schools is the vocabulary and notation. We teach kids, how do you add fractions? You find a common denominator, you make equivalent fractions, you add or subtract the numerators, you bring down the denominator, and you simplify. Well, then how do you add decimals? Well, decimals are fractions. So how do you add decimals? You find a common denominator, you make equivalent fractions, you add or subtract the numerators and bring down the denominator. Except we don't say it that way. What do we say? We tell the kids when you're adding decimals, line up the decimal points and fill in the zeros. Why? Because you found a common denominator and made equivalent fractions. Then you add the numbers. That's adding numerators. But you bring the decimal point straight down, you're bringing down the denominator. So the point I want to make is, as the kids progress through math, the biggest changes are the vocabulary and notation. The concepts and skills stay the same. The verbiage changes clearly. And because in algebra, we're able to see patterns a lot quicker. So a minute ago, when we learned how to multiply binomials horizontally, I think we had a problem. I can't remember what we had. We had a problem like 2x plus 1 times 3x plus 2. And we said you multiply the 2x times both of these numbers and the 1 times both of these numbers. Well, now if I have a problem like 104 times 103, what will happen is you see a pattern. 104 is 100 plus 4 times 100 plus 3. 100 times 100, that's going to have 4 zeros, so that's 10,000. I'm going to have 300s plus 400s, that's 700s. And I'm going to have 3 times 4, which is 12. So 100 times 100 is 10,000. 100 times 3 is 300. 4 times 100 is 400. 4 times 3 is 12. So 104 times 103 is 10,712. So if I gave you a problem like this, what's 102 times 106? If you saw a few of these develop, 100 times 100 is going to be 10,000. I'm going to have 2 plus 6 hundreds, that's 8 hundreds, and 2 times 6 ones, or 12 ones. So that answer is 10,812. Now I can hear you right now. You're saying, hell, I want to do one. So go ahead and do 104 times 105 in your head. It's going to be 10,000. You add the 5 and a 4, 900, and then 5 times 4 is 20. So this answer is 10,920. Okay. Again, the nice thing about math, it is so connected. You know, how many of you teach FOIL? All of you, good. So you have a problem like 32 times 21. Whoops, except you can't see it. Please tell me that, could you see what I was doing multiplying by hundreds? Was I on the right screen? Thank God.
Yes.
Okay, if I don't, let me know. Whew, it scared me to death there. So multiplying by FOIL, 2 times 3 is 6. The first, first, outer, inner, last. So the first times the first, 2 times 3. The last, 1 times 2 is 2. The ooey is like the stuff inside a Twinkie. You start to eat the Twinkie and the stuff gets on your fingers and you go, ooey. Okay, that's the outers. There's 3. There's the inners. That's 4. 3 plus 4 is 7. The answer is 672. So that, the nice thing about algebra is patterns jump out at you. So if I wanted to multiply crap like this, I could do it mentally. And hopefully what you're doing is when you're teaching, you're using mental math. Now, in a high school algebra class, you teach something called an arithmetic sequence. And you define an arithmetic sequence as a sequence in which every term after the first is obtained by adding a common difference called D. And whoops, here's the formula. A sub n equals a sub 1 plus n minus 1 times D. Now let's go find the nth term of an arithmetic sequence. Can you imagine being a 13, 14-year-old and having your teacher drop that on you? Are you kidding me? Okay, we call it an arithmetic sequence. Now it's spelled the same way you spell arithmetic, but don't call it an arithmetic sequence. It's an arithmetic sequence. It's kind of like you don't have a photographer come to your house, you have a photographer come to your house. So get the accent in the right spot. What is an arithmetic sequence? 2, 4, 6, 8. Who do we despise and hate? 5, 10, 15, 20. When are arithmetic sequences taught? They're taught in first and second grade. What's it called? It's called skip counting. Okay. So if I look at that, that's what we do. So you're teaching an arithmetic sequence in algebra, and it sounds like, for a kid, they're going, holy crap, it's a sequence in which every term after the first is obtained by adding a common difference called D, and then you give me this damn formula? Are you trying to fail, kids? Okay, now, little kids learn to skip count by counting in multiples. Like I said, 10, 20, 30, 40, but we don't have to count in multiples. What we could do is count, give me a first number, and let's say I'm going to add 5s to it. So let me get back to my screen. So if I have a problem like 8 as my first number, I add 5, that gives me 13. I add 5, that gives me 18. I add 5, that gives me 23. And I say, I wonder what the next number is. And that's what they do in little kids' school. So the kids go 5 and 5, and they get 28 here. Isn't that neat? So if I had a problem like 2, and I decided to add 10, that would be 12, 22. And then what I could say is, what would be the next 3 numbers? And the kids would go 32, 42, 52. Pretty cool, huh? Now, what I could say is this. My common difference in this one is 5. So I take my first number, which is 8. I add 5 to get 13. I add 5 to get 18. I add 5 to get 23. And I add 5 to get to 28. So this was the 1, 2, 3, 4. This is the 5th term. So for me to find the 5th term of this sequence, which was the next term, how many times did I add 5? I added 5 4 times. Kind of interesting. Now, let's say I wanted to get to this term. That's the 1, 2, 3, 4, 5. That's the 6th term. So if I said, how many times did I add 10 to get to the 6th term? Let's see. I started off with the 2. I added 10. I added 10. I added 10. I added 10. and I added 10. 1, 2, 3, 4. I added 10 5 times. Now, I'm going to do one more, and then you can tell me what this is going to be. Let's say I start off with a number like 3, and I add 7. So that's 10, 17, 24. And I say to you, what is the 8th term of that sequence? Well, let's see. That's 4, 5, 6, 7, 8. So I'm adding 7, I'm adding 7, I'm adding 7, I'm adding 7 to get 31, I'm adding 7 to get 38, I'm adding 7 to get 45, 1, 2, 3, 4, 5, 6, 7, and I add 7 to get to 52. So the 8th term, how many times am I adding 7? I'm adding 7, turns out to be 7 times. Now, if we did enough of these, here's the pattern that, and again, I'm not giving you time to do this, but you'll notice if I'm looking for the 5th term, I'm adding the common difference 4 times. If I'm looking for the 6th term, I'm adding the common difference 5 times. If I'm looking for the 8th term, I'm adding the common difference 7 times. Oh my God, we see a pattern. So in terms of doing this, if I give you this sequence here, 4, and I'm going to add 8. So 4, 12, 20, 28. And I say to you, what is the 21st term of this sequence? Well, hopefully you're not going to draw a bunch of lines and do this. What you're going to do is you're going to look at this and say, my common difference is 8. And from this pattern over here, it looks like I'm going to add 8 one less time than the term I'm looking for. So I'm going to add 8 20 times. So I'm going to add 160. But what am I adding 160 to? The first term. So it's going to be 160 plus 4. On my 21st term will be 164. Now tell me, isn't this a blast? I mean, how easy does this crap get? All right, let's just do one more since you're having a good time. Let's say I have a problem like 3, and let's go ahead and add 11. So 14, 25, 36. And I ask you to find the 101st term. Are you going to draw out all those little lines and add your little brains out? Hell no, you're not, because you just saw a pattern. So what are you going to do? You're going to add 11. How many times? 100 times. So that's, just so you know, 1100. And what are you going to add that to? 3. You're going to add it to the first term. So it's the answer is 1103. Now, let's write that algebraically. If I ask you to find, let me rewrite this. You know, we just said we had this 3, 14, 25, 36. So here's what we did. We were adding the common difference 100 times. So the common here, let me say that again. We're adding the common difference, which was 11, and we're adding that one less time than the term I'm looking for. So 101 minus 1 times. So in doing that last problem, I'm adding the common difference one less time than the term I'm looking for, since I'm looking for the 101st term. And what am I adding that to? The first number. So this turned out to be 3 plus 100 times 11, which is 1103. Now, how do we write that? If I ask you for the nth term, I generalize that. So what I'm going to do is I'm going to take whatever my common difference is, I'm going to multiply that by one less term. So if I'm looking for the nth term, I'm going to multiply by n minus 1. So I'm looking for the 21st term. I'm going to multiply the common difference by 21 minus 1. And what am I going to add that to? The first term. Well, this is an arithmetic sequence. So let's use A for arithmetic. And let's say I'm looking for, this is the first term. So I'm going to use a subscript 1. So I have this formula. I'm going to take whatever the common difference is, multiply it by one less term I'm looking for. Why? Because I'm seeing that pattern. And what am I going to add that to? The first term. So now I have this beautiful formula that says, defined it as a sub 1 plus n minus 1 times D. And now I'm looking for the nth term, and whatever that term is, I'm just going to call that A sub n. So rather than dropping a formula on the board for the kids, you'd go through a bunch of these examples. I don't know what the hell I do with them. Well, what did I do with them? There they are. You'd go through some of the examples that I now can't find. Oh, there you are. And start to see a pattern that if you were looking for the sixth term, then you'd be adding the common difference 5 times. If you were looking for the fifth term, you'd be adding the common difference 4 times. So what we do is we generalize that and say, if I'm looking for the nth term of an arithmetic sequence, and that's why we call it A, that's going to be the first term plus n minus 1 times D. So if I say, let's say I give you this sequence here, 12, 9, 6, 3, and I keep on going. So now I'm getting smaller. Okay, so what's my common difference here? Minus 3. So D is minus 3. So my formula is, let's say I'm looking for the, 31st term. If I'm looking for the 31st term, I have A sub 31 equals A sub 1 plus n minus 1 times D. So what is my A sub 1? It's the first term, which is 12, plus I'm looking for the 31st term. So it's going to be 31 minus 1, and the common difference is negative 3. So in terms of doing this, this is 12 plus 30 times a negative 3 is negative 90, and 12 minus 90 is negative 78. Okay, so my point is this. The formula is pretty easily derived once you see that pattern. And it's, whether D is a positive number or a negative number, whether it gets smaller or larger fractions, it doesn't matter. What we did is we saw a pattern develop and we developed some notation for that. Now, oftentimes, okay, let me stop there. I need to put my glasses on to see what the hell I'm doing here. Okay, it's 2:37. Mike, Mike, you're there. What time am I getting done?
2:40. You had 3 minutes.
Oh, crap. Okay, I'm done. I'm not going to go any further. Sorry about that. People, let me just say this to you. If you're looking for classes, go to the rpdp.net website. And I offer generally 1 or 2 workshops per week. And you get, depending, I guess, on your school district, you get units for that, CUs for that. If you go to my own website, which is hanlonmath.com, I have all kinds of resources. There are videos, there are chapters, and there are worksheets. The worksheets typically have a problem strategy or formula with a worked out example, and then with problem sets. And because I typically work with struggling students, I use nice numbers, as you should when you're introduced, particularly on initial instruction. Sorry, I didn't take any questions, but that's how I roll. Anyway, I thank you for attending. Appreciate it. That hour went too quick. Thanks.
Thank you very much, Bill. And we appreciate your wonderful presentation. I'm sure a lot of our participants appreciate your expertise and talent in this one.
Okay, just so you know, I'm full of it. All right, you guys have it. Thank you very much. I really do appreciate it. My website is hanlonmath.com. Everything on there is free. There's no usernames or passwords. Feel free to use that stuff. If you have a substitute, the videos would be nice because they're about 20 minutes long. They tell the kids what to write down, or write the title, the date, the objective. It goes through the definitions, identifications, how to say it, along with how, with the development of the procedures, and then work problems. Thanks again.